What's up, AP Precalc? Mr. Messer here. Talking about Unit 1. Unit 1 is all about like, hey, what's going on with the graph? You know, we kind of looked at specific functions, but we're just going to look at just random functions. And we're going to start talking in the next 2 units about like, what do our functions look like? Okay? So like overarching like 1/2 is like, what's going on with our functions? Unit 1, focusing more on like, how are my functions changing? You know, how is it going up? Is it going down? How quickly is my function going up and going down? So that's kind of like this unit. Like unit 1/2 is what's going on with functions, specific types of functions. Unit 1, we are going to focus on how are my functions changing. And we talked about in class how we can just like subtract numbers like 57 and 55, 57.1 and 55. And if you do 57.1 minus 55, you get 2.1. And you'd say, oh, my function W went up 2.1. Cool? But what the problem with that is we're not going to be able to compare this 2.1 with maybe what goes on from 57.1 to 61.8. You know, it's like, oh, I went up 2.1. And then by subtracting these two numbers, you could say, oh, I went up, that's 4.7. Oh, I went up 4.7. Oh, I must have gone up more here. Well, the problem is you can't compare these two numbers without context, okay? And what we are going to do is find rates of change, a specific amount of increase per X, or amount of increase per input. So we don't just subtract the top, we divide it by the interval in which we did that increase or decrease. So we did increase 2.1 Ys, but we increased 2.1 Ys over 4 minutes. I'm going to do the division. We don't technically need this, but it's like going to help. And I'm going to be able to say, oh, from 0 to 4, my W increased 0.525 degrees Fahrenheit per minute. Degrees per minute. It becomes this rate of change, and a rate of change is a way to be able to compare how quickly functions are changing on different intervals. Okay, so like if I go from 61.8, from 57.1 to 61.8, I did increase 4.7, but to compare this number to the interval from 0 to 4, we want to look at how much we increased over my interval. So over 5 minutes, I increased 4.7. Now, I still believe that's going to be a greater value than from 0 to 4, but just saying like we're able to compare these two numbers. From 0 to 4, W increased 0.525 degrees per minute. From 4 to 9, W increased 0.94 degrees per minute. Okay, so like that's kind of like an introduction to what we're doing. We're just finding like comparable rates of change. Okay, and we're starting you off with a real world situation. In my class, I started you off with just like Y's and X's, but then we transitioned to real world. If Hoffaker's class started you with real world, then transition to Y's and X's. This real world situation, it's all about like the change in your Y's over the change in X's. You know this as slope. So rates of change, we are going to define as slopes. Okay, rates of change are slopes. So we're going to find the change in our Y's over the change in X's. Here, the change in my Y's would be in degrees Fahrenheit over the change in x's, which would be minutes. We'd be able to see we are increasing this many degrees per minute on average. We are decreasing this many degrees per minute on average. Okay, now we want to find the average rate of change of each subinterval. So subintervals are just like, hey, from 0 to 4, what is going on? From 4 to 9, what is going on? We already did 0 to 4. So we got from 0 to 4, on average, the temperature in the tub increased 0.525 degrees per minute. From 4 to 9, on average, the temperature in the tub increased 0.94 degrees per minute. We're going to give you easier values to calculate, so don't stress about like, oh, how did you get 0.94? Oh, are we going to be given a calculator? It's like, don't stress out about that. Use a calculator for now, but like, you'll be fine. From 9 to 15, let's do the math. 67.9 divided by 61.8. Sorry, wrong. Subtract to find how much the net change is what we talked about. Subtract to find the net change. I can't do this. I increased 6.1 degrees Fahrenheit. I'll do the work over here. This is from 9 to 15. I increased 6.1 degrees Fahrenheit over an interval of 6. To find that, you could do 15 minus 9 to get 6. Over an interval of 6 minutes, 6.1 degrees over 6 minutes is 1.016. We'll just go 3 decimal places. Degrees per minute on average, okay? So we'll say from t equals 9 to 15, my temperature in my tub increased because we had this positive net change over this time interval, increased 1.016 degrees per minute on average. And then from 15 to 20, I'm turning off my brain right now just so I can get this quickly. 3.1 over 5 minutes, 0.62. On average, the temperature in the tub increased 0.62 degrees per minute, okay? When do we think the temperature in the water is increasing the fastest? Now, we don't know for sure, but like we talked about, if you're analyzing change, use as many subintervals as you can so you could see like how quickly the function is changing at different intervals, and like the smaller the interval, the more you're gonna know. If you have a table of information, you only have a limited amount of intervals, just use as many as you can and make the best guess based on what you see in your data. And we could see that from 9 to 15, we would assume, or we would speculate the temperature in the water is increasing the fastest. I'm not going to write that down. This is the greatest rate of change comparing all of the rates of change. Okay? Now, we go to just like y's and x's, which is what I introduce like things with. Like a function, this function is going up and down and up and down. We can look on average how it's changing, maybe over a big interval. If we want to see when it's changing the fastest, we're going to try to look at small intervals, as many intervals as possible. It's all about how are my y's changing over how are my x's changing. We want to find the net change in the y. We're going to find like the future function value and subtract the initial function value. We'll take our future x, initial x. Slopes give us comparable rates of change. So, starting from -1 to 8. This line, its slope shows you the average rate that this function is changing between -1 and 8. It's not changing at that rate consistently. It's just on average. See, the function goes up and then goes down it's good to see that line. It's not necessary to do the calculations. We went up 7 to find that. It's like I ended at 6. I came from -1. I increased a total of 7. Over the course of 9 x's. I went up 7 over the course of 9 x's. We would say, on average, my function is increasing. Now, we're not going to say 7 y's over 9 x's. We're going to make this a rate of change. We're going to make it a y's per x. And what I do is put this value over a 1. So we say, on average, my function is increasing. I'm not going to change this into decimals because we have whole numbers. On average, my function is increasing 7/9 of a y per x. Okay, these are my y's, these are my x's. You could say these are my y's and x's, but I like to kind of make it a rate of change, a unit rate of change. From 3 to 5, this is a shorter interval, so we have a better understanding of what's going on with our function. We could see maybe we're slowly increasing faster than increasing less. We can find on average how quickly we're changing by finding the slope of that line. y2 minus y1 over x2 minus x1, or changing my y's increased from 1 to 7, so I went up 6. You find that by subtracting 7 minus 1. I went up 6 y's over the course of 2 x's. That can be simplified to be 3 y's per x. On average, my function is going up 3 y's per x. I forgot to say over the interval. Over the interval -1 to 8. I could use this, but it just takes too long. On average, my function is increasing 3 y's per x over the interval 3 to 5. Okay, I'm going to go faster. I think we understand the explanations, so start going faster. From 1 to 3, here's our first, maybe I got to go slower for this. Here's our first situation where I will get a negative rate of change. My function is decreasing. I ended at 1. I started at 5. It's very important to say it's 1 minus 5, okay? My net change is negative. I decreased. My y's decreased 4. This is over the interval from 1 to 3. 3 minus 1, 2. That gives me -2. An average rate of change is negative, meaning my function is decreasing on average. My function is going down on average. So let me just write that. On average, my function f of x is decreasing. You can use an arrow for shorthand. 2 y's per x over the interval 1 to 3. All right, 1 to 6. Great. From 1 to 6, we can see there is no change in my y. On average, I don't increase nor decrease. I'm constant. Now, my function does go down and up, but it ends up at the same place where I start. So on average, there is no increase or decrease. My function was constant. Again, it's on average over this interval. So I get like 5 minus 5, which is an increase of 0. 6 minus 1, 0 over 5 is 0. On average, my function was constant over the interval 1 to 6. Okay, cool. All right, now we have equations, and we want to know how these equations are changing. Well, you're just going to be finding the slope between 2 points on this function. You need to kind of not create the entire graph. You don't need to graph everything. All you need is to say, like, okay, where did you start, where did you end, and find how the y's changed over the course of the interval of the x's. So plugging in 2, I get 4. Plugging in 5, I get 25. Well, my y's increased by 21 as my x's increased by 3. So that's a total of 7. On average, f of x goes up 7 y's per x over the interval 2 to 5. Okay, negative x cubed. Make sure you're not messing up on things. I'm starting at, if I take negative 1 and cube it, it's negative 1. Take the opposite of it, it's positive 1. If I take 3 and cube it, it's 27, but take the opposite of it is negative 27. So I start at 1, I go down to 27. I decrease 28. This is very important. It's like where I ended up minus where I started to get our net change. Make sure your net change is negative, or rather, make sure your average rate of change is negative. My function is decreasing. Start, finish. Finish minus start. 28 divided by 4 is negative 7. So negative 7 on average. I'm going to write this one more time and then I'm going to stop. On average, g of x decreases 7 y's per x from negative 1 to 3. Cool. I'm going to just say the statement, but I'm not going to write it down. Where do I start? I start at 3 plus negative 2. I start at negative 1, 1. Where do I get to? I have 16 times 3. I got to do that on the side. 48 plus a half. Thanks. Okay, well, I mean, let's go. Let's do it. 48 times 2. 96 halves. 96 halves plus a half is 97 halves. 97 halves is where I ended. I started at 2 halves. Over the course of 5 x's changing, I get 95 halves over 5. What do we do with fractions? Dividing is the same as multiplying by the reciprocal. 95 halves times 1/5 is 95 tenths. I could divide 95 by 5. It's going to be 19 because 5 times 20 is 100. So 19 halves. 19 halves over 1 can represent our rate of change, our unit rate per change. On average, my function is increasing 19 halves y, or like 9.5 y's per x. Where did I start? At 3. Where am I going? To 1. Plugging in 2. 2 plus 1 is 3. 3 over 3 is 1. I decrease 2. Make sure you can calculate that. I think probably most students' errors is not listing things in the right order. I always like to have my x's go from the smaller to bigger. So it's like it's always going to be the bigger minus the smaller. And then just keep things aligned. You know, I always like to do my finish minus my start. If you do start minus finish and you do it consistently, it will work out. But I always like to do like end minus start for our net change. I went down 2 as I increased 2 x's. On average, my function decreased 1 y per x from 0 to 2, g of t. Oh, cool. You guys remember fractional powers? They're not disappearing on you. 1 to the 2/3 is 1. 8 to the 2/3. What's 8 to the 2/3? You guys, some of you just never like jumped on the way that we did it in class. I saw it on your tests. Like we split this into a root and a power. 2/3 can be written as 1/3 squared. Some of you kept doing squared then a third. Like you would use the root notation. It doesn't help you because you get like a big number and then you got to know the cubed root of a big number. It's like, that's not easy. I know the cubed root of a small number, like the cubed root of 8 is 2. 2 times 2 times 2 is 4. 2 times 2 times 2 is 8. 2 squared is 4, so this is 4 times 5 is 20. My y's increased 15, my x's increased 7. You do not have to show the work, just get the right answer. On average, my function increased 15/7 y's per 1x. Big G of 4. Again, I'm splitting this into a fractional power first, then the whole number power. So that would be 9 to the 1/2 cubed. Square root of 4 is 2. 2 cubed is 8. 8 times 4 is 32. Square root is 9 is 3. 3 cubed is 27. 27 times 4 is 108. 32 to 108, that's 76. Over 5. You don't have to do the calculations, guys. Like, you don't have to. You can just kind of look like 32 to 108. 76. 76 y's per 4 to 9. 5 x's. 76 fifths y's per x. If you have a calculator, it's easier to see that. Like 76 fifths are like, we are increasing 15.2 y's per x on average for this function. We are understanding what the function's doing. We are understanding what it looks like. On average, it's going up. Here's how quickly it goes up. Info. This is good stuff. We can do this without a calculator and without graphing, okay? Last couple. Small h, 3. 7. 6. 10 fourths. Okay. 5 halves. Let's make sure that's at 6 plus 4 is 10. 6 minus 2 is 4. Okay, so 7 to 5 halves. So 5 halves is where I ended. I started at 14 halves. What did I do? I decreased 9 halves over the course of 3 x's. Division is the same as multiplying by the reciprocal. You could multiply straight across or divide the top and bottom by 3, canceling the 3, turning the 3 into the 9 into a 3. Negative 3 halves. On average, h is decreasing. It's going down. I think for you guys it looks like this. It's going down 1.5 y's per x. Cool. Where did I come from? Where am I going? Oh, this is a fun one from Mr. Huffaker. He made this homework. On average, I don't go up or down at all. 126 minus 126 is 0. On average, I'm neither increasing nor decreasing. I'm constant. 0 over 10. Over the interval, h on average is constant. Cool. All right, now we talk about specific rates of change of specific types of functions, and we analyze rates of change of very specific functions, and we notice something was in common for 2 different types of functions. Starting with linear functions. From 5 to 7, I increase 2 over, from 0 to 2, 2 x's. 2 y's per x, my rate of change, I'm going to say my average rate of change for f of x is 1. 7, 8, 1 over 2. My average rate of change is 1/2 y per x. 8 to 0. I decrease 8 over the course of 2 x's. I'm decreasing 4. 6 to 8, I'm decreasing 15 over the course of 2. I'm decreasing 7.5. from 6 to 8. 8 to 10, I'm decreasing 5. Decreasing 5 over 2, I'm decreasing 2.5. This is a neither. Linear function, the rates of change are always constant. Like, think about a linear function. It's got a slope. Well, that means between any 2 points, I'm going to have the slope of that line. So if you have the equation, say, y equals 3x plus 2, and you had a table that created 3x plus 2, and we did this in class, you notice that the rates of change are always 3. That makes sense. What we find in quadratics is that the rates of change in a linear function, in a linear manner. It's like you will see the average rate of change create a pattern, and the pattern is a linear pattern. We will talk about like how those rates of change are changing in day 2. For right now, we're just going to say that the rates of change of a quadratic are linear. This is neither a linear pattern nor is it constant, so this is just like some random function. It's a neither, it's a random guy. Let's go down to these, and then we'll come back to this one. I go down 1 over 2x's. So average rate of change is down 1/2. I go down 3 over 2x's. My average rate of change is minus 1.5. I go up 5 over 2x's. Should say 1.5. I go up 7 over 2x's. 3.5. Okay. Pause. I made a mistake. Down 1, up 3. Okay. Made another mistake. Up 1. I increased by 1. Come on, Mr. Messer. All right. Now we're seeing what we're supposed to see. Sorry about this. -5 to -4 increases by 1. I should have just done the math. Anyways. You see your average rates of change are 1/2, 1.5, 2.5, 3.5. You notice that there's this pattern that you're increasing by 1. The rate of change of the rate, or like the rates of change are linear in nature. That is how you establish, that's a quadratic. We'll talk about how you will look at like the second rates of change or the rate of change of the rate of change. And if those are constant, boom, you have a quadratic. Let's look at this guy. All right, let's make sure I get this right. I go down 4 over 3. Down 4 over 3. Down 4 over 3. Down 4 over 3. These are the rates of change. I'm not going to change them into different values. These are the rates of change of this function over our different intervals. We can see those things are constant. Boom, you're linear. If you don't see a consistent pattern of rates of change, it's a neither. It's a rando. If there is a consistent linear pattern of the rates of change, it's a quadratic. If the rates of change are constant, it's a linear. This is the slope of the graph. You could even write the equation y equals, or f of x equals, -4/3 x plus some value. We could actually use one of these points to find this value, and boom, you have the equation. Okay, this is great. We got a quadratic. That's good. So you're told it's a quadratic. Well, that means my rates of change must be linear. This is a good problem to do. So let's find these average rates of change. We got 2/3 here. We are going down 1. This we're going down 6 over 3. So that's down. That's down 8/3. Sorry, it's -1. Okay, my rates of change have to be consistent. I'm going to change this into thirds. My rates of change don't have to be consistent, but they have to be consistently changing. They have to have a linear rate of change, if that makes sense. To go from 2/3 to -3/3, I'm going down 5/3. To go from -3/3 to -8/3, I'm going down 5/3. That means the next rate of change has to be down 13/3. Okay, 8, 9, 10, 11, 12, 13. Okay. If my rate of change is 13/3, I have to go down 13 over the course of my 3 x's that I've traveled. Well, I already got 3 x's here. Now I just need to take my y's and go down 13. So that would be -1, subtract 13, go down 13, I get -14. You can check, boom, like -1 to -14, down 13/3. That would fit in the linear pattern where the rates of change, the linear pattern of the rates of change. 2/3 to -3/3 to -8/3 to -13/3. Fun. Last page. Okay. Okay. This is different. Here's the position graph, and we're moving along the x-axis. I didn't know if we want to do this motion. I don't think I would stress out about this for your quiz, but it's cool. Let's do it. When are we passing through the origin? It's when my position equals 0. I'm just going to take this equation, set it equal to 0. I will factor to solve. I'm not going to explain too much because I don't want to get too much in depth into what's going on with the situation. So at 3 and at 5 are the times when my object is at 0. Okay, average rate of change from 0 to 4. Okay. I started at -15. I ended up at 16 minus 32 minus 15. So that's -16 minus 15, which is -31. Okay. So I started at -15. I ended up at -31. -31 minus -15 shows me that I am decreasing by 16. That's a -16. So we could say on average, my position decreases by 4, units per second, if t is in seconds. Okay, now what we're trying to get at is that if you are on the x-axis, this one-dimensional x-axis, and your position goes from -15 to -31, on average, you have to be moving to the left. We get in a lot to position graphs in calculus, so maybe this is just an intro. I wouldn't stress out about it much. No. When does the object meet its leftmost position? Well, let's think about what's happening. We have a starting position of -15. We will have It should be like rightmost position. We have zeros at 3 and 5. Oh, I was wrong. Darn it. Shoot. Did I have to use the quadratic formula for this? It's only 5 and 3 or 15 and 1. It's not negative 5, negative 3 because then it'd be positive 15. So, I don't know. 4 times 1 times 15, negative 15, 15, 30, 45, 60. So that's going to be plus 60. Jeez. Okay. 4 times 31 is 124, so I got 2 root 31. So I get 4 plus or minus root 31. I was wrong with this graph. Root 31 is a little bit less than 6. My vertex is at 4. The object starts at negative 15, will decrease till negative 31. It will have a 0 here and here. This is root 31 away from 4. So you can see the position graph like this. What time did the object reach its leftmost position is at 4. It ends up being the minimum position when the position is most negative. This is just a challenging problem. I don't think we're going to worry about this for our quiz. It was a good challenge. If you're in physics, maybe that helps you. 8 and 9 though I like. 8 and 9 are good. We got a quadratic. We got from 1 to 4 and from 4 to 7. We got T and P of T. We got the average rate of change of P of T. The average rate of change of P of T from 1 to 4 is 5. From 4 to 7 is 2. From 7 to 10, if this is a quadratic, the average rates of change need to be linear in nature, which means like we have to subtract 3 to get the next rate of change. You're going to have to go down 1. So the average rate of change must be 1 y per x over the 3 x's. So you have to decrease 3. If you're talking about negative 2 to 1, the average rate of change is got to be minus 3 to get to 5, which means it must be coming from 8. Now, what's great about this, guys, is if I give you, this is the average rate of change of P of T. If I give you one value of P of T, say like P of T started at 2, you can fill out the rest of the values of P. And this is kind of what the next problem is. Okay, I'm going to show you this example here so the next one makes sense. If you know we started at 2 and you have an average rate of change of 8, well, you're increasing 8 y's per x, or 8 p's per t, from negative 2 to 1. So that is over an interval of 3, negative 2 to 1, I'm increasing 3. If I do 8 y's per t, and I started at 2, I need to increase 24 to get to 26. Okay, 26 minus 2 is 24. 24 divided by 3, boom. 8 y's per x, p's per t. You could continue to do that if this is 26, and between 1 and 4, the average rate of change is 5. Well, I'm increasing 5 y's per x. I have 3 x's that are increasing, or 3 t's. So that's increasing 15. So 26 plus 15 is 41. Boom. 2 y's per x, p's per t, over 3, 2, 4, 6. I got to increase 6 to get 47. And then from 7 to 10, I'm decreasing 1. So I need to decrease 1, 2, 3. So that gives us to 44. Now, double check to make sure that this table fits with this table. 26 minus 2 is 24 over 3. 24 over 3 is 8. 41 minus 26 is 15. 15 over 3 is 5. 20, 36 plus 5, 41. Yep. 41 to 47 is 6. 6 over 3 is 2. 47 to 44 is minus 3. Minus 3 over 3 is minus 1. Okay? Because that's what kind of we need to do for some of these situations. If you know the average rate of change, you only need one value to fill out the rest of the table. Okay? So if the average rate of change between Q, between 0 and 2, is minus 2 over 2, which is minus 1. This is the average rate of change of Q. From 15 to 18, we're increasing 3 halves, so that's 1.5. If this is a quadratic function, the average rates of change must be changing consistently, changing linearly. I must be increasing by 2.5, or increasing by 5 halves. So this would be a total of 8 halves. 2.5 plus 1.5 is 4. Okay, cool. This is 4 y's per x. I've covered 2 x's. 4 y's per x would cover a total of 8 y's over 2 x's. 26 must be the missing value. Okay? Some of this stuff is confusing, but if you just kind of go with it in practice, you'll be fine. I wouldn't worry so much about this position. This is a good little test question. Like, as in we're seeing, like pushing your envelope here. Not that this is going to be on the test. I'd focus more on finding rates of change, making sure you can interpret them. Rates of change make things easy to compare. Okay? Y's per 1x. Positive rates of change, functions increasing. Negative rates of change, functions decreasing. As many subintervals as you can, the more information you know about your function. All right? This is a good homework. Nice and long. I'll see you out there.